professor Roberto Ferreira. Estou aqui para colocar para vocês vídeo 18. Laboratório virtual de extrusão, fabricação e recuperação de roscas. Apresentar para vocês na continuação de extrusão uns vídeos bem interessantes. Um sobre um laboratório virtual de extrusão, é um software criado pela Compuplast. Ele vai explicar diversos módulos ali de como resolver problemas em extrusão, como projetar, né, softwares amigáveis. É interessante quem puder ter na sua empresa. É bem intuitivo de utilizar e explica várias coisas. Depois também tem um vídeo a respeito de produção de roscas, mais voltado a mostrar o tratamento térmico de cilindros e de roscas. Um outro a respeito de uma manufatura de rosca, mas é um sistema diferente esse aí, eles agregam um material de aço duro através de solda para formar o filete de rosca. Normalmente as roscas são usinadas completas de um tarugo, fazendo o próprio filete. Nesse processo eles fazem um canal e eles aderem por solda um material mais duro para a região do filete. Depois eles usinam todo o canal da rosca, fazem o tratamento e cromagem. E tem um último vídeo que é a respeito de uma rosca de PVC bem comprida, uma rosca grande, e ela quebrou em 3 pedaços. Então o pessoal utiliza de engenharia reversa, porque não tem nenhum projeto da rosca, nada. Eles simplesmente pegam os pedaços quebrados para fazer medições e poder usinar um pedaço novo e acoplar no pedaço que sobrou da rosca, na quase totalidade da rosca, que ficou boa, porque o que quebrou foi na zona de alimentação, onde tem mais torque ali, né? E por degradação do PVC, e foi degradando o aço e rompeu. Então vamos aos vídeos.
Okay, welcome everybody. My name is John Perticoulias. I'd like to give you a presentation here, basically a brief overview of the Compuplast Virtual Extrusion Laboratory. And I'm going to do that through really more so some applications. Actually showing the software, in my opinion, is somewhat boring, but really giving people an appreciation for what you can do and what sort of problems you can solve, I think will give you a better understanding of what it's all about. This fellow here, Jerzy Wilczek, is my business partner and one of our main developers who looks after our development team over in Europe. So the objectives here is introduction to a virtual extrusion laboratory, demonstrate the application of VEL towards extrusion, show how simulations can be used to troubleshoot, optimize an extrusion process, and explain certain observations or phenomenon with the aid of simulations that would be very difficult to understand otherwise. And most importantly, the correlation of simulation with reality. This is the key to using simulation properly and becoming efficient. Understanding what the pictures on the screen mean with respect to the reality of the process and the problem you're experiencing. The virtual extrusion laboratory consists of these process simulations, and we have a custom one here if the particular situation doesn't apply. And now, in reality, the virtual extrusion laboratory really consists of about 12 modules, and the following parametric modules are going to be offered through Polymer Ohio. These will be the material module, which has the material database and allows users to enter material data and fit it and use their own materials. The extruder module for single screw extrusion simulation, a screw design and optimization. The flat die module for simulating flat or cast film dies, including feed block type co-extrusion dies. The side-fed die module, which is for crossheads type dies for annular coating or cable and so forth. Spiral die module, which is a spiral mandrel distributor, typically used for the blown film process, but also found success in pipe tubing and even blow molding. And the flat spiral die module is something that's relatively new. It's used for distribution systems similar to the spiral die module, but on a surface of a disc, which provides certain benefits, particularly in multi-layer co-extrusion dies, let's say over 5 layers. And of course, then we have the multi-layer module, which is used to analyze and design co-extrusion systems where you have layers of multiple polymers. These modules were selected because they are really the easiest to learn and use, because the data is entered as parameters such as length, gap, depth, diameter, radius, etc. And the calculations are mostly based on a control volume technique, which is accurate but also very fast. So you can be much more efficient in your calculations. Now, the Virtual Extrusion Laboratory also has additional modules which are finite element method based. And these are our profile die module, our 2D FEM module, and our 3D FEM module. So this is fully 3D and fully 2D calculations. And these require you to create a grid and so forth. We also have a chill roll module and a cooling module, and we may be adding the chill roll module to the polymer portal because I think that one's also relatively easy to learn. The cooling module is still also based on finite element analysis, and this means that we can build the geometry within the module, but that's rather inefficient. Rather, what you do is you import a CAD file, or start with a CAD file, create a mesh, and then import the mesh to perform the calculation. And unlike the parametric modules, which will give you the answers on the order of seconds or within minutes for solution time, you're looking at many minutes up to hours in calculation time for finite element type modules. Perhaps not with 2D FEM, but it does require a little better understanding in how you're creating the meshes and performing the analysis. So generally, these modules will require more training, and we may eventually add them to the polymer portal, depending on the requirements and user demand. So I'd like to begin with the Virtual Extrusion Laboratory extruder module, which is applicable to just about everybody in extrusion because they generally start with an extruder. And it's used to simulate single screw extruders and optimize screw designs. It's capable of simulating conventional or barrier type screws with multiple flights. It includes various mixing sections such as the Maddock mixer, fluted mixer, or spiral fluted mixer, or called Egan mixer, pineapple type mixers, blisters, etc. And it's been applied to thousands of screw designs worldwide, so it's a tried and proven simulation module. What I'm going to show you is how we would use it to analyze a particular problem. And here, this is a film sample that experienced periodic shower gels. So as you can see here, there are little particles in the product, and these would happen periodically. Like you would go along fine, producing good product with uniform color and no defects, and all of a sudden you would get a shower of these blemishes and imperfections inside the film sample, and the customer came to us and asked, can we help them try to determine what the problem is? And typically, whenever you have something that's periodic, I mean, the extrusion process is supposed to be steady state, and so whenever you have a periodic variation, we typically search for something in the extruder screw. It doesn't necessarily always have to be at that point, but that's the first place we look. And the first recommendation is to actually pull the screw and take a look at it. And in this case, here's the extruder screw that was used on that process. And you can see immediately the discoloration in the first half of the screw. There's much higher discoloration, whereas in the second half, the screw is relatively clean. You can see the chrome polishing on it. And in particular, if you notice, the discoloration is particularly high right at this point here, which happens to be the compression area of this particular screw. So just a little background, and I don't know how well you're going to be able to see these videos, but these are some videos from a glass window extruder. The flow direction is in this direction here, so from right to left on your screen. So here we have an extruder screw, and the feed section is right up here somewhere. So we have pellets coming in and getting compressed. This is what we refer to as the solid bed. As the pellets get compressed, they form a solid bed. And then somewhere right here, you'll start to see a little bit of melting. It's more clear over on this screen, the melting. That clear area where you can see the screw, it doesn't mean that it's empty. When the polymer melts, because it's amorphous, it's clear, so you can see right through it, and you can see the root of the screw. And also, here you can see the flights on this side, but over here you see a little bit more part of the screw, and that's the melt pool that's being generated. And that material continues to melt, and the solid bed continues to get narrower until ultimately it disappears. Now let's zoom in a little bit on another window here. So here we see the solid bed and and I'll just pause it for a second here, right there. So here's the solid bed, and here's the melt pool in the screw channel. And as you proceed along, you see the solid bed gets narrower, and the melt pool, of course, gets wider to accommodate the molten polymer. And over here on this side, what we'll notice is that the solid bed is discontinuous at some points. So you can see it disappears. Now let's zoom in on that side of that particular slide. So here it is here, and I'll just pause it for a second so you can see. You can see that the solid bed here, it's almost gone, and then you'll see it'll appear again. There it disappears here, and then it disappears over here. So disappears over here. So this solid bed has broken for some reason, and this particular screw, there's no mixer to compensate for this breakup of the solid bed. And so solid material, once the solid bed breaks, the polymer gets encapsulated, the pellets get encapsulated in molten polymer, and now they don't experience the shear at the barrel surface that results in the melting. And as a result, they just have to melt by conduction, which is, of course, very low because polymer is an insulator. And so one of the parameters that we analyze in the simulation is the so-called solid bed ratio. And this is simply the ratio of the solid bed width versus the overall channel width. And as you can imagine, the solid bed ratio starts at a value of 1 because everything is solid back in the feed section. And then this gradually reduces down to 0 prior to the end of the screw, or it should anyway. Now, let's take a look at simulation results here. So we simulated this particular screw, and I'll lay the screw down on this graph so you know what we're analyzing here. So this is the relative distance along the screw from 0 to 1, and this is the graph of the solid bed profile. And the solid bed profile, as I mentioned, starts off at a value of 1 in the beginning of the screw in the feed section, and then at some point the material starts to melt. So you see the solid bed is reducing gradually as the material is melting. And then we notice something strange in this particular screw. Right about here, which coincides with the dark area on the screw, the solid bed actually starts to increase again, and you think, well, this is strange. Why would the solid bed be reducing and then start to increase? Well, what's happening is that the solid bed ratio is a linear measurement. That is, it's based on the width of the solid bed relative to the width of the channel, but it doesn't take into account the compression. And in the screw here, as you can see, the feed channel is deeper than the metering channel, and somewhere in here we have the compression. And as you compress and squeeze the solid bed between the root of the screw and the barrel, if you are compressing faster than you are melting, then you will spread out the solid bed. And so that's what it shows here, is that the solid bed starts to spread out. And we know now from experience that whenever we see a result like this, where the solid bed profile isn't, or solid bed ratio isn't reducing continuously down to 0 and starts to increase, that we are putting more force on the solid bed and compressing it faster than it will melt. And that's a condition where we rupture the solid bed and create solid bed breakup, right? So once we understand this and we run a simulation and we see a graph like this, we want to adjust the geometry or the process conditions or perhaps even the material or something so that we have a graph that is more like this, where we have continuous reduction of the solid bed, and so that it goes to 0 well before the end of the screw, so the screw can perform some mixing beyond this. And of course, adding a mixing section will also be beneficial to homogenizing the material a little bit better. So moving on to the next example here, I want to talk about screen changers, adapters, and I'm going to talk with respect to a flat die just because the geometry is easier, but pretty much all dies. Whenever we analyze the flow in these sections, we want to study certain characteristics in the flow field to see whether the geometry is acceptable. So for example, at the end of the screw, we have a screen changer, and quite often when people add screen changers to extruders, the screen changers typically require some distance prior to the breaker plate for the pressure in this area to load the seal section. There's usually a sealing section in here, and it requires some distance to create enough force to create the seal. And they don't accommodate for the length of the screw, and so they have a large empty area in here. And they want to make it easy to pull the screw if they ever need to pull the screw, so they don't have a reduction in volume here. And so if they wanted to pull the screw, they just index without a breaker plate in there, and then they can pull the screw right through the screen changer. However, if you do a simple calculation in here, you'll see that the extruder sizes, the bore diameters, are so large relative to the flow rate that you're not going to get a very good flow characteristic. And just to demonstrate that a bit, or explain that a little bit more, I'm going to introduce you to the wall shear stress. The shear stress on the wall is equal to the viscosity times the shear rate. And this is a very, very critical parameter in having good performance in the equipment. When you have some velocity profile or material flowing through a tube or through an annular gap or any flow channel within a die, you end up with a certain shear stress profile in the system. And the shear stress is minimum where the velocity is maximum and is maximum at the wall. So you have a graph of shear stress. If this was 0 here, you would have a maximum shear stress of the wall going down to 0 at the high velocity point, and then again up to maximum stress on the other side. And it's this shear stress that is used to keep the surface clean. It's what determines the self-cleaning characteristic of the wall, because this shear stress actually scrubs the surface. And the big question is, what's high enough to keep that surface clean in my equipment? Well, through many years of experience and studying different pieces of equipment and conditions, we've figured out that a critical value for shear stress is in the neighborhood of about 30 kilopascals for polyolefins and maybe 35 kilopascals for PVC. Now, just for your U.S. numbers here, 30 kilopascals is equal to about 4.3 psi of shear stress. So once you understand how important this value is to maintaining a clean surface, what happens if you don't maintain a high enough value is that you actually get a layer of polymer not moving along the surface, just being stagnant. And eventually it will degrade and come out. Once it gets, the layer gets big enough, it will start to get scrubbed by the material flowing in it. Or if you do a heat change or something that will disrupt it, and it'll come up and appear as a gel or some degraded material in your product. So we want to avoid any condition that has this low shear stress. Well, one of the first tools and one of the most powerful tools in the virtual extrusion laboratory is within our material module, and it's called the extrusion calculator. The extrusion calculator allows you to perform relatively quick calculations on some of the most common geometries that appear in the extrusion process. So here you see a slide showing the calculation that I did on that barrel section. We have a 90 millimeter diameter tube, basically, with I just picked a length of 100 millimeters, 250 kilos per hour, and 190 degrees Celsius. And I'm using a 1 mi film material. And when you perform that calculation, over here we have the flow characteristics of that particular flow field. And we can see that our shear stress is showing at 8.9 kilopascals, and our shear rate is 1.38, 1.4. Now, this is one of the unique features to the virtual extrusion laboratory, and I don't think any other software analysis software for extrusion has anything like this. We have checking parameters for each polymer group, and the checking parameters are used within the modules to highlight potential conditions where there are problems or potential problems in the system. So just to kind of demonstrate how this works, I'm just going to bring over the software here. So this is kind of a live demo, and I'm going to go through the design of an adapter. So you want to design an adapter, let's say, to convey 150 pounds per hour of polyethylene at 390 degrees Fahrenheit. And let's say I'm a junior engineer. Adapter length, we'll say our adapter length is 16 inches. And let's say I'm a junior engineer and I'm not sure what this size should be, so I pick a 2-inch adapter, and then I perform a calculation. Well, the software here will show me the velocity profile, the pressure drop through that adapter, 51 psi, average, maximum velocity, residence time, but it'll also highlight two numbers, the shear rate and the shear stress. And when I put my mouse in that box, it'll pop up a little window saying the shear stress should not be less than 4.35 psi. With low shear stress, the scrubbing force on the wall may be low and the material can degrade. Now, that is a warning to the user saying, hey, your design condition is not very good. So the user can choose to go back and say, oh, let me try 1.75 and perform the calculation again. And we say, oh, it's still not enough, the values are still low. And we got kind of tired of this, so we added this nice little button right here. And when you click on this, it automatically changes this to the optimum channel size that avoids the problem with the minimum shear rate and shear stress. And now this is a kind of odd drill size, so we would probably go 1.125 for the 1 1/8 for our adapter size. So the shear stress gets a little bit higher, shear rate's a little bit higher. And of course our pressure drop is higher through our adapter. We got about 260 psi through that adapter. But the flow conditions are such that we're not going to have stagnation of the material or channeling of the polymer through that adapter. So the extrusion calculator is a very, very powerful, quick tool for sizing channels and checking to see if part of your degradation problems are not properly sized channel. Very similarly, here is a photo of a damaged flat die, cast film die. This was for PVC. And what you see here is the metal of the die has actually been etched away. PVC, when it degrades, it forms hydrochloric acid, which can get under the cracks of the chrome and erode away the metal. And a lot of die manufacturers make a good living off just repairing and rebuilding these dies continuously because of this degradation that occurs here. Well, if we analyzed this geometry, and this is the flat die module now. This is a result from that module. And what I'm showing is the shear stress on the surface. And this is actually the way we determine the critical values for shear stress for a particular polymer. Here, the shear stress you can see in the manifold, that would be this section right in here. This shear stress in this manifold is varying from a higher value here, somewhere in the neighborhood of about 50, down to a value of about 10, 11, somewhere down in here. And so when we graph this this result, we can get a graph, something like where you see the degradation matches the low stress area. But when we graph this, we get a graph of the stress across the width of the manifold. And so what we do is we go back to a certain distance and say, okay, the degradation appears to start right about this point, and we can do the same thing on the graph. We can move back to about that point on the graph, in the position of the graph, and we say, what's the stress level right there where we see that it's still acceptable? And we find the value here of 30 kilopascals. So we say, okay, we're going to say that for PVC, we're going to use a value of 35 to give us a little bit of leeway, and that in the next die that we manufacture, we're going to design this manifold so that the majority or virtually all the manifold has a shear stress above this value, or 35 kilopascals, to avoid degradation. And so when you have the simulation, you can perform those calculations relatively easily and then have an iterative approach to doing those types of calculations. So for polymer degradation, one of the main parameters that we need to address is the shear stress on the walls. And this has to be adequate to avoid stagnation of the material and degradation. And this means proper channel design and sizing, and also proper operating conditions. The best designed channel and highly polished and designed for 200 pounds per hour will not be adequate if you're only running it at 100 pounds an hour. So you have conditions where people say, you know what, yeah, design it for 200 pounds an hour because I'm going to get a larger extruder later, and but for now I can only run 100 pounds an hour. Well, that doesn't do you any good for now because you're going to have stagnation problems and degradation. So with the virtual extrusion laboratory, you can calculate those things quite easily. Now here I want to demonstrate a particular problem that was rather challenging and probably almost impossible to determine without the use of simulation. This demonstration here will use the finite element software to analyze the problem and understand it. Once we understand it, then we can use our control volume or spiral die module that's on the portal to design equipment and avoid the situation, because we can correlate this observation to that module. And I'll show you how we do that. So the first thing is we're getting these strong lines appearing on the bubble, and they're very, very sharp lines on a blown film process. Now I've seen this also on a pipe process, and I've seen it also in blow molding. So it's not limited to blown film, but in blown film you're typically making a clear product and it's more visible in that product. And this is done on a spiral mandrel die which is basically a die that has helical grooves cut in the surface to distribute the polymer. And the polymer comes into the die through these ports and then gets distributed around by flowing through these helical grooves. Well, these dies, these lines that we observe are very localized, thin sections that repeat around the circumference equal times as there are spirals. Many times there are spirals. So everybody, directs the problem to the spirals because that's how many of these problems there are. Now here's a geometry of a die. This isn't actually one of the real geometries because they were proprietary, but once you understand the problem, you can create it almost on any geometry. So here I've made a die that has roughly similar characteristics, and because of the periodic nature of this geometry, we only need to analyze one section between ports. So you can see here that we have basically in this die 3 inlets, and so you can see that this one section repeats basically 3 times. So to make life easy, we always take advantage of any periodicity. We take advantage of any symmetry. Anytime you're doing calculations, especially finite element type calculations, where you want to, you're going to have you need a lot of memory, a lot of computer time, you want to minimize that, you take advantage of any sort of symmetry or periodicity. So that's what we do here. And just to kind of give you a better idea of the flow field, I did this video a few years back. So this is a 100 millimeter die with 4 spirals. So it's a 4-inch diameter die here. It's got 4 spirals, and I set it up on a rig where I could pump some silicone fluid through it. And I used a clear acrylic body so we can see what's happening. And there's a 1 millimeter gap between the ID of the clear acrylic body and the OD of this mandrel, which is consistent. So I just took some Dow Corning silicone fluid and ran it through, and you can see the material coming through there and flowing around and coming out. And if everything's designed right, you get a uniform annular flow at the exit. So you can see the material flowing in, and then as it flows around, the gap between the mandrel and the body allows it to leak out, and you have the uniform annular flow. So that's the flow field that we're studying. And now here is a result from a finite element simulation. So you can see the finite element mesh, the outlines of it anyway. This is showing pressure. And the pressure contours look fine. There's nothing particular here that will indicate a line being produced on this product. And here's the velocity distribution. Velocity coming in here. Blue at the wall is 0 because the velocity is basically very, very low at the wall. And then here we can see the velocity at the exit. We see slight variation in the velocity. And it's kind of a gradual variation, but nothing to indicate that there's going to be a problem with a weld line or the appearance of a line again. And if we put 2/3 of the flow field together, now you can get an idea a little bit about the periodicity and how the material flows, but you have this velocity, slight velocity variation, but like I say, not a lot, nothing to indicate there's a weld line. Now, here we show the shear stress, and the shear stress gives us the first indication of a potential problem. We see that there is a localized minimum, like the shear stress is relatively high here, and then it drops to blue right in here, and then it gets slightly higher again here, and then drops again a little bit here. And it indicates that there could be a potential problem in this localized low stress region. And so we analyzed this flow condition using particle path lines. And this is one of the big advantages of doing a 3D finite element analysis, is that you know the velocity everywhere in the flow field, and you can study path lines, kind of similar to streamlines, but in 3D, where you can say, okay, I'm going to start from here. Here's my seed particle, and you tell me where this material flows out through the die. And so that's what I'm going to show you here is a series of images of that. So here's the first one here. I've started from this point right here, and you can see how the material flows through this flow field and comes out at this point here. Now what we're going to do is put a series of points around the that inner wall there of the starting point. And that, if we follow those points around and then connect the dots at the exit, we'll have an idea of where the material from this inlet ends up at the die exit. So here now is 2 points. There's the one beside it, flows a little bit further. We'll go through the next one here goes a little bit further. Then we put the next point. The next point, we see that it doesn't go much further, actually. It comes out a little bit sooner, ends up almost on top of the other one. Next point here, this one from over here goes a little bit further. Next point from up here comes back, comes out a little sooner. So you see we're not getting much flow out in this area. Now this point right here, it comes out, almost comes straight up out of the die, close to the entrance area. And this one's the most interesting one. This one comes out quickly and goes out this area. Now because of periodicity, another one appears from this side and ends up coming up here. And we put another one right out here. And we see this one does the same. It comes out this end and enters from the other side and shows up here. Now, the really cool thing about finite element analysis and path lines is that you can do something that you can't really do in reality. In reality, we could set up a rig and inject some material here and watch it flow through the system. But in finite elements, we can do the reverse analysis. We can actually put a particle here and say, where does it end up? So if I click there, this particle would come from here. So from this point here, where does it come from? It comes here. And if I click over a little bit further, and this particle, trace it back, it comes out here and then comes from this point over here. Now, it's not really coming from the same channel. What's happening is because of the periodicity, these particles are coming from the next spiral. So if you were to look at it together, this is what's happening. The material from the next channel is coming back, flowing in here. The material from this channel is flowing up to here. And we have a region right in here where the material is avoiding or not flowing in. And this region, if we put the shear stress on here in transparency, we see that the low stress area is the area that the particle paths are avoiding. Now, if we look at it again, combined now with two of the three sections, we can see it more clearly. And this right here becomes a weld line that would appear in your final product. Now, when you're looking at a die on the line, you don't have the advantage or the luxury of seeing through the die to actually see the particle lines and the path lines to see this. So without 3D simulation, it would be very, very difficult to solve and understand this problem. However, once we do understand the problem, which is material leaking out too early from the channel or too soon from the channel, then we can go to our spiral die module, and this is a result of the spiral die module that is on the portal showing a simulation of this geometry. And if we look at a particular result which is inside the channel in the channel direction, and we do the flow along the spirals item, we see a graph like this, and we see a local minimum and then an increase again. And whenever we see a result like this in the spiral die module, we know that it is a bad design and it's going to result in a stagnation area. And we can see a similar effect from the mandrel stress on the surface. Again, that's what this graph down here is plotting the shear stress on the surface. We see that there's a local minimum again in here, and this, whenever we see a condition like this, we know that this is a problematic design, and we should correct it. And the correction would be to control the leakage flow from the spirals to ensure adequate velocity, and again, shear stress along the entire channel. And so a result like this, where the flow along the spiral does not drop dramatically, drops kind of more gradually, and the shear stress on the mandrel remains relatively high for the majority of the distance. Of course, at the end, it has to reduce because the flow in the channel is reducing. But this is a much, much better condition in the design, and this is what we would prefer to manufacture as opposed to what the previous result was. So in conclusion, I wanted to say the process simulation provides more information for correlation between process conditions and production problems. It gives you a new insight or a window into the process so you can see the problems and understand them. And once you understand the problems and what's causing them, this leads to a more precise solution or perhaps avoiding them altogether on a new design.
Vamos ver agora um vídeo de produção de roscas, tratamento térmico e cilindros também. Aí um cilindro indo para tratamento térmico, né, no forno. Usinagem de rosca. Ó, essa aqui é a maneira como se faz a usinagem do cilindro dentro, é com mandrilhamento, tá? Então a superfície do cilindro fica áspera com esse tipo de usinagem. Ela fica num diâmetro preciso, mas não fica com polimento. A rosca é polida e o cilindro fica áspero. Esse é o mandril, mandrilhamento. A usinagem de um cilindro dupla rosca. Aí está a dupla rosca. Ó. Normalmente, aqui aparece as dupla roscas. O cilindro normalmente é segmentado, tá? É feito em pedaços flangeados, mas com precisão, certo? O tratamento térmico, controle de qualidade e tal, e aí aparecem as roscas. Bom, vamos adiante aqui. Essa é a produção de uma rosca, sendo que eles fazem um caminho, um canal, para agregar material, um aço mais duro no filete da rosca, para depois usinar os canais.
So how does it really get from this, a rusted hunk of metal, to this, a finished product ready to make a number of products we use daily? As you might imagine, there are many steps to this process.
They come in all rusty and stuff. They just look like they came out of a cast pretty much.
So you've got a lathe operation in which you're turning that down to a precise bar because it's just a rough piece of steel when it comes in here.
And so we have to turn them down so they're more round because they come in and they look like eggs. They're not round at all.
And once it's been turned to a particular size, it will go into one of our milling machines. And at that point what we do is a process called channeling. And essentially what that does is that lays a deep channel all the way down the outside diameter of that bar of steel. So you'll have something that looks like a river channel or whatever you would want to think in terms of a channel that goes down the entire length of that screw in a spiral fashion.
The screw actually spins the parts you're machining. It turns, your cutter spins, and then it follows a lead, and it makes like a corkscrew style.
And we put hard-facing alloys and fill these channels, and that becomes the top of the flights on the screw. And the reason that you do that is that when this goes into operation in melting plastics, that's a very hostile environment, very abrasive environment. And if you didn't put carbide alloys on the surface of the flights, these things would wear out in a couple of weeks.
It's like, I mean, it's really hard stuff. We can't machine them Like once it's welded, we have to grind it down because it'll just break cutters.
So what happens at that point is it'll go into the welder, it'll be welded, it then goes into a tank of vermiculite, which will slow cool the screw. At that point, it may stay in there for 2 or 3 days depending on how big the screw is, and the process there needs to slow cool because the weld that is put into the channel has a different rate of cooling than the base steel.
The weld is all uneven, and they have to fit inside of a barrel, which it can only be off like by hairs. So like about 5 hairs on your head. I mean, and we're talking the weld when it comes out of the welder is, you know, it could be off 1/4 inch. So we throw them in the OD grinders. OD is for the outer diameter of the screw. And we have certain tolerances that we have to take the OD down to.
Once the hard facing is welded on it, then we actually cut away the steel that becomes the channels of the screw. And that's done on a very, very sophisticated machine, and we are the first people in North America to have purchased a machine that actually is what they call a dual slide machine. It was manufactured in Austria, and it does both the milling function and what they call whirling. You actually have 2 different slides, and you park one slide, and so you're either milling or that you're whirling. And that's how you remove the metal and create the channels in the screw.
At that point, it will come out of the CNC machine. It'll go over to one of our belt polishing stations, which looks like a big belt sander. It'll start at a heavy grit and go down to a finer grit through that process. What we're trying to do is take all the imperfections out of the bar steel at that point. One of the things that plastics hate is anything that's a rough surface, so that it'll want to stick to and then degrade. So we get a very fine polish on that, on the screw at that point. Probably 95% of our screws are chrome plated, so that's the polishing process that happens right up until the chrome plating. When it comes back from the chrome plater, we will buff it and final polish it. We will also put the drive end on the screw. There are various different milling operations that go into the fit and finish for the actual machine that it will be going into.
Por último, aqui um vídeo de uma rosca que quebrou em 3 pedaços na zona de alimentação, uma rosca bem comprida, com um LD bem grande, para extrusão de PVC. Ela sofreu degradação pelo PVC e quebrou. E o pessoal fez um trabalho de engenharia reversa aqui. Ó, eles pegaram a amostra aqui quebrada, né, e fizeram um desenho, pegaram um tarugo para usinar. Uma coisa que eu quero observar para vocês já de cara é que nesse tarugo aqui, eles já fizeram uma rosca na ponta. No restante da rosca que está inteiro, eles vão fazer uma rosca fêmea desse tipo para enroscar uma parte na outra, e depois eles vão fazer um bisel para fazer uma solda e recuperação da rosca toda. Tá? Então o que está acontecendo aqui? Eles fizeram a trilha de onde vai o filete, né? E agora eles estão fazendo a fresagem por etapa e vão girando essa peça e fresando ela toda. Eu vou passar adiante aqui porque é todo um processo semelhante, tá? Ó, eles vão fresando ela, retirando o material, né? E aqui tem um acabamento todo, né? Vamos um pouco mais adiante aqui.
you on the next video. Subscribe and like, please. Okay, the easy part is done. Got it nicely roughed out. Most of the material is out. Did it 4 different setups, 90 degrees apart. Very rigid. And now the hard part.
Bom, o que ele falou? Que a parte mais fácil foi feita, né? Tá no ângulo adequado aqui, os filetes e tal. E que agora é a parte mais difícil que eles vão partir, que é a parte mais árdua, que seria do acabamento, né? Então esse filete tem que casar também com o restante do filete da rosca lá. Vamos ver adiante aqui.
Finishing it.
Agora estão procedendo um acabamento melhor nessa parte, depois vamos fazer o acabamento da rosca inteira, depois de soldado.
Brought in just a wee bit damaged. My job was to reverse engineer the old one, make a new model, and then machine a new one. Still got some hand polishing to do. But I'm pretty happy with the results. From this to this. Okay, thanks for watching. Subscribe if you like the video.
Aqui aparece agora a peça roscada já na peça que permaneceu boa, daqui para lá a rosca tá boa, e vocês vão ver depois na continuação que tem um LD bem grande. Aí eles fazem casar bem o filete aqui, abrem um bisel, que eles retiram o material, fazem a solda, e aí eles vão terminar um polimento total dessa rosca para, de repente, uma posterior cromagem, né?
Screw during polishing.
Estão realizando o polimento da rosca toda agora.
After welding. Many hours to go. Hand polishing.
Bom, seria isso aí. Eu creio que está bem interessante, estão bem interessantes esses vídeos aí para dar uma ideia de que a gente pode ter dentro de uma empresa um estúdio virtual de extrusão para resolver problemas que são de um acesso bem simples. E também a parte de construção de roscas, como é que pode ser feito, e a reconstrução, né? Estou sempre à disposição nos meus e-mails para tirar qualquer dúvida que possa ter ficado. Não se furtem de me consultar. Um abraço a todos.